Hello, this is a lesson for class 8, and this is a lesson on the Earth, Sun, and the Moon. That is movement of the sun in the sky, the nighttime sky, the movement of the stars, eclipses, and seasons, formation of seasons. So you are encouraged to use a lot of day-to-day observations. So it is helpful and better if students and teachers actually take the trouble to make small observations in their surroundings, like the point of the sunrise each day over a period of several months, the shadows, the behavior of shadows every day, and so on. So let's get started with the lesson. This is the lesson: seasons, movement of the sun in the sky at various latitudes on Earth, stars at night, their movement at various latitudes, and then moon and the eclipses. So since the ancient times, people have observed the sun, the movement of the sun, the formation of shadows, the change in the length and the direction of the shadows, and the seasons, the changing seasons, the change of weather according to the seasons. So all these are small observations which you can make in your immediate surroundings. And they use these small observations to get a perspective on our place in the universe. So it's easier to get a perspective. The perspective, I mean the big picture. Okay, so if you are living in a small colony in a city or in a little village, then you know the layout of your neighborhood. So you know there's a road here, school there, and all that. So you can just walk around and get a big picture. If you know village, then you know where the fields and the homes are. So that's easy. So, but to get the big picture, you have to do a lot of work. For example, we know so for example, when we see the map of India, you see that the Himalayan mountains are laid out like this. So this is the big picture. So, but this is not what you see when you actually go to the Himalayas. This is what you see. You see boulders, hills, valleys, like this. Okay, so from this, if you want to go to that map, the picture in the map, then you have to do a lot of work. So people survey, they travel hundreds of kilometers this way, that way, measure, record, and then you find out what is the uh, shape of the Himalaya mountains on the map of India. That this is the shape. Okay, you get it after a lot of hard work. Similarly, when it comes to our place in the universe, so our ancestors, the old people, people in the old long back, they could get this the big picture after a long time, after a lot of observation, and then by studying these observations closely. What are those things which you can observe day to day? Uh, Small details that you observe. So the first observation is, of course, day and night. We all know that day follows night within 24 hours. Now we know, with our knowledge of about what Earth does and where it is, we know it rotates. The Earth rotates, so you face the sun and you face away from the sun. So you have day and you have night. Then the next observation is a cycle of seasons. So humans have observed the seasons, the coming and the changing of seasons. over many thousands of years. So now we know that the seasons happen because the Earth revolves around the Sun, and it has the axis of rotation is tilted. So because of this, we know that seasons happen. So let's see how they happen later. And they also observed, people who traveled in the ancient times, they observed that seasons are more pronounced in different parts, in some parts of the world. So you have in some parts of the world that winter is very severe, whereas the other parts of the world, the winter is very mild and warm. So this is another observation. So you and me, what can we observe? So if you go out in the morning, out of your home, you can see where the sun rises. Okay, so we all have some landmarks in our surroundings where we live. For example, those are the landmarks where I live. So there's a tall apartment building to the right. There's a coconut tree here somewhere. There's a smaller house to the left. So as the seasons change, the position of the rising sun changes slowly. So in March, that is in spring, sun rises behind this coconut tree and goes up in an arc like that. And every day, the position of the rising sun changes, moves to the right slow gradually, and um, by June, it would have shifted to this place. Okay, so every day it changes, it goes to the left. I'm sorry. If I start in March, then by June it ends up rising from behind this small house. So every day the position changes. So and then between June and September, again it comes back. The position of the rising sun changes again, and slowly it comes back. And then in September, again the sun rises from behind the coconut tree. And then October, November, December, it moves towards the right side, that is towards the south. Okay, so gradually every day the position changes, and in December, the sun rises from behind this large apartment building. Okay? So this is to the south, and that is to the north. I can check this using a compass. Okay, so this is an observation we all can make using some familiar landmarks. So this is the movement of the sun. It rises in east in September, or in March, let us say, and then it moves towards the north. No, it moves towards the south. So this slide is wrong. Just ignore it. So we have seen what it does. Similarly, the other observation people make is the shadows. So in a single day, we know early in the morning you have long shadows, and the shadows are all slanting towards the west. Sun is in the east, the shadows are all slanting towards the west. And as the sun goes up, the shadow becomes smaller, and at one point, it's the shortest. So the shortest shadow, if we observe every day, it will lie strictly in the north-south direction. We'll see this again later in the lesson. So, and then towards evening, the shadow becomes long and it becomes slanted towards the east. Sun is in the west and shadows slanting towards the east. So, in a single day, you can make this observation. Okay. So, there are other observations that you can make relating to the shadows. We will see that as the lesson proceeds. Okay. So, we need to know how shadows behave, not just on a single day. We need to know how they behave throughout the year. And we also need to know how the shadows behave on different parts of the earth. Okay. So, with all these observations, people in the ancient times, they use these observations to conclude that we live on a planet which is round, which is a sphere. We live on a planet which rotates, on a planet which revolves around the sun, and so on. Okay? But now we will start in the opposite direction. We already know, we have been told that the earth is a sphere, it rotates on its own axis, It goes around the sun in 365 years, sorry, 365 days approximately. And there are other planets which revolve around the sun. All these things we have been told by our teachers, in our textbooks, and we've also seen pictures, okay, from uh, you can see satellite pictures of the Earth, pictures of the Earth from the moon. So all these is very much familiar to us. So we will take these what we know, knowledge of these things, and then understand why, why we observe what we observe. Okay, why does this the rising location of the rising sun change gradually every day? So other observations like that, we will understand the reason for it. These are the shadows early in the morning, around 8 o'clock in the morning on a winter day. These pillars are all vertical. We know that pillars of any building are always vertical. So they're all the shadows are slanting towards the west, and you can observe that all these edges, edges of the shadows, are all parallel to each other. So all the pillars cast shadows in the same direction. Now this is the shadow of the same set of pillars around 10 o'clock in the morning. So the shadow has shrunk. It is not slanting so much towards the east, and the length has decreased. So let's see what happens 1 hour later. Now this is around 11:30 before the noon. So the shadows have become even smaller, and but you see their edges are all still parallel. The shadows, because they are all vertical objects, the shadows will always have edges which are parallel to each other. This is around 12 o'clock. So this is the shortest shadow of the day. Okay. So and they're all pointing forward. So direction has changed very much. Now I want to see what direction does the shadow lie. I want to go close. Okay. So this is a compass needle. I'm using the compass needle. Actually, you should not be, this is only approximate, but still, it tells you that the edge of the shadow now is along the north-south. Okay, so it's pointing towards the north. This edge is the north. So the shortest shadow of the day lies in the north-south direction. We can check. This is how we check. Now, after another 1 hour, then the shadow will lengthen and again become longer. Now, this is around 3 o'clock in the afternoon. So now the shadow is tilting towards the east, and it has become very long. So so the length has increased again. So we all know that this is what happens. So what we have found out here from this activity is that the shortest shadow of the daytime, it points in the north-south direction. So now let's come back to the lessons. So we know, what is it that we know? That's the Earth revolves around, the Earth rotates every 24 hours. The moon is the Earth's satellite. It goes around the Earth every 28 days. Then the Earth revolves around the sun and in an elliptical orbit. And all the other planets revolve around the sun. They all lie in a plane. Their orbits lie in a plane, which is known as the ecliptic plane. So let us just look at all these things uh, one by one. So what is an ellipse? An ellipse is a shape like this. So uh, here we have got different kinds of ellipses. One of them is a perfect circle. A circle is also an ellipse. Then we have some very long and thin ellipses. So how do we draw an ellipse? So this is how we draw a ellipse. I first fix these two thumbtacks on a this is thermocol sheet. So they have to be fixed so that they don't move. Then I take a string which I have tied in a loop. Then I put the loop around these uh, pins and then hold them in place so that they don't move, and draw the string tightly and trace it with the pencil so that you're drawing an ellipse like that. So this is the ellipse, and this is how you draw it. Now that we have drawn an ellipse, we can ask ourselves what are the properties of the points on an ellipse. A circle is all where the points are all equal distance from the center. So you can ask what how do the what is the property of the points on an ellipse. You can also make a paper cone and cut it obliquely. So you take a paper cone, cut it obliquely like this, and look at the edge. So you can dip this edge in ink and make oval marks on the sheet on a sheet of paper. Those are ellipses. So by cutting it in different directions, you get different ellipses. Okay, so now next let's look at a globe. We use a globe as a model for the Earth. Okay, so the globe has the latitudes, the longitudes, and all. Let's just look at it carefully once. So this is a globe. So it has the globe spins on an axis. So these two metal points here at the top and at the bottom, which are inclined, slightly tilted, those are the poles of the axis. The North Pole at the top and South Pole at the bottom. And there is the scale here which shows the angles. So the central part of this is the you can see the black line which is the equator. Okay, so that equator divides the Earth into northern hemisphere and southern hemisphere, and you can see the longitudes which are going from pole to pole, and the latitudes are parallel to the equator. So the Earth spins like that. So that is those are the two poles. And the axis is tilted. This is the vertical, so that is just holding up. So to the axis is tilted at 23 degrees to that vertical. So as you take a closer look, you can see these markings. So they're marked in degrees. Okay, from 0 to 90. The North Pole is 90 degrees. Let's see where our country, where India is. India. So you can just rotate it, bring it close to the scale. Okay, so those are the latitudes. The parallel lines are the latitudes. So India is somewhere around uh, close to 0 degrees. So close to the top equator, maybe 10 degrees, maybe, and then up to 30, 32 degrees, so on. Okay, so these are that's the North Pole, the North Pole, and this is the Southern Hemisphere, 90 degrees, South Pole, and these are the longitude lines. You can see the lines, these are the longitudes. So we have now seen the globe, and now let's see the orbit of Earth. So we said the Earth and the other planets all revolve around the Sun, and the orbits lie in the same plane. So these are the ellipses. Each ellipse is the orbit of one planet. So now that you've drawn an ellipse, we needed two fixed points to draw the ellipse. So this uh, red ball there is the Sun, and it's I have placed it at one of those pins. Okay, and then the first ball here, that is Sun. This is Mercury, Venus, and Earth. So Mercury goes round like that. It does not rise up. Okay, it sticks to the sheet, same plane. This is Venus, that is Venus, orbit of Venus. So it does not rise up, it just goes along the plane. This is Earth with the moon. Okay. So the moon's axis is tilted, it's in a different plane. So that is why I have a small sheet of paper sticking out of the thermocol sheet. So this is the ball is Earth, and the moon is going around it, and that the moon orbit of the moon is in a different plane, which is inclined to this thermocol sheet. This is the plane of the planet. All the planets, the moon's orbit is slightly inclined. Okay. So we need to remember that moon's orbit is slightly. So that's one half of the orbit I have shown. The rest of the half lies beneath this plane. Now, this plane can be extended. All the 9 planets will revolve around the sun in the same plane. So I can extend this, imagine, and extend this sheet of thermocol to fill the entire room. So that is the plane in which the solar system lies. All the planets revolve in that plane. So the Earth spins around the axis on the tilted axis, and that is how day and night form. So this candle is the sun. So one half of the Earth is facing the sun, it's daytime, and the other half is the nighttime. So if I switch off the light, you can see this demarcation between day and night. Okay? So the portion of the Earth which is in the sunlight, one half of it, that's daytime, and the axis is tilted. So we have seen this plane in which all the planets orbit. It's called the plane of the ecliptic. Why is it called plane of the ecliptic? We will understand that later. Then, okay. So now we've seen that the Earth revolves, the Earth rotates every 24 hours on an axis which is close to 23 degrees to the plane of the orbit, to the orbital plane, the ecliptic. Okay. So now what is an axis of rotation? What do we mean by an axis of rotation? So here I have a cardboard cutout of a figure, and it's attached to a pencil at the along the midpoint, the midline. So when I spin it between my fingers, okay, so the figure is rotating. So you can think of yourself uh, stretching out your arms and rotating around yourself. So what you notice is that these arms, okay, they move through space. The tip of your fingers, they move through the space as you spin. They move a lot. Okay, whereas the central point, the head, it doesn't move. The top of the head here does not move. It just stays in the same spot and goes around. So same thing when you stretch your arms and you rotate around yourself, your head and the feet don't move. There's this So all these points which don't move, but which just turn on the spot. This is where the axis is. The axis. So now the end of this figure is attached to the pencil. So the pencil is the axis of rotation. Okay. Okay. Now if I tilt the pencil, then the axis has changed direction. Okay, so now the figure is rotating in a different direction. The axis has changed its direction. I tilt it further. Okay, so the axis has a direction. So the pencil was an axis, or in the globe case of the globe, we had this the metal point as an axis. You don't need to have a pointed axis. So here is a ball which is spinning, okay? And when it spins, there is an axis. So all those the and how do we know where the axis is? Those points on the ball which just simply rotate where they are without moving through space. We just rotate. So that is the axis of the spinning ball. Okay. So the Earth spins, it rotates, and it spins around an axis, and the direction of the Earth's axis is fixed in space. Okay, so as the Earth moves around the Sun in the orbit, the axis of rotation does not change direction. So, okay, so for any heavy or massive body object, when it rotates, it's not easy to change the direction of its rotation axis. You have to apply a large force to change, you have to force it to change direction. So since nobody is forcing Earth, it keeps spinning in the same direction and maintains the direction of the axis throughout. So let's watch what we mean by that. So this is a setup. So this the sheet of thermocol. This is the Earth's axis, Earth's orbit. So the Earth, this globe, goes around this oval shape. So here, at this, when it is here at this point, this the plastic refill here is parallel to the Earth's axis. So that's the direction. Okay. So, but when the Earth goes to this point, the next point here, then that the other sheet of the other plastic refill is the direction of the Earth's rotation axis at that point. So which is parallel. Okay. So as the Earth moves around the Sun, the axis keeps its direction. So I have not changed the direction of the axis. The axis is still pointing in the same direction. These two plastic refills are strictly supposed to be parallel. They may not look so because I have not fixed them perfectly. And similarly, when it goes to the other end, so from there, when it goes to this side, this end of the orbit, okay, so what happens then? So then the Earth's axis is pointed like that. Okay, so sorry. So this is, so now these two lines are strictly parallel in space. Okay, so the Earth's axis has not changed its direction. So it does not change its direction when it goes around the Sun. The axis maintains its direction. So I can look at the Earth's axis. So this is the same sheet, and I have stuck these pins. So this is the various points in the orbit, and the pin shows the direction of the Earth's rotation axis. So they're all parallel to each other. They're pointing in the same direction in space. So that is how one can visualize the axis of rotation. It does not change direction. Does not change direction. They're all parallel to each other. No matter where Earth is, this axis points in the same direction. So as the Earth is floating in space, the axis of rotation points in the same direction. And because of this, because the Earth's axis maintains its direction and because the axis is tilted, okay, so we have seasons. So, okay, what happens in season? I mean, what are the various things which affect happen during when the seasons change? Between summer and winter, the length of the day changes. So, if you're in the north hemisphere, the day is longer than night in summer, and day is shorter than the night in winter. And this difference changes with the latitude where you are. So, we are going to understand that. Now, before we do that, first we need to find out, answer this question. It's very important for us to understand what follows. Okay? So, here I have two diagrams. This is the sun, and the light of the sun is coming and falling on Earth. So, which of these situations is true? Does it do the light? So, the light rays travel in straight lines. So, they all these straight lines are the light rays, they're coming and falling on Earth. So do they fall like this as in the first diagram, or do they fall like this, which is as shown in the second diagram? Okay. So which of these two is true? You need to pause here and ask yourself this question and try to come up with the answer. Which of these is the actual situation? Why? Okay. Why is it the way you say it is? Okay. So you pause here. Okay. So now so, this is an important question. Okay, so okay. Let us hope that you have thought about it and you come up with the answer. So, what is the answer? The answer is that second diagram is the correct situation. Okay, so here because the sun is so very far from the Earth, all the rays which are reaching the Earth from the sun, they have started almost in the same direction. So that so you see, so this bunch of rays is almost on this in the same direction, and slowly they diverge over this distance and then cover the entire Earth. So and you can see that the rays of light which are reaching Earth are all almost parallel to each other. So whereas in this other diagram, the rays are fanning out. Okay, the rays in the center of the Earth, the rays of the poles, they're all fanning out. So that's not how we're going to look at it. We're going to look at the situation like this. So the sunlight reaches Earth in all the rays, they come in almost parallel to each other. Okay, so now as the Earth moves in its orbit around the sun, I am taking the two extreme positions. One is the summer, one end is the summer, and the other end is winter. Okay, so so when in summer, since the axis is tilted, the north pole is tilted a little bit towards the sun, and south pole is tilted away from the sun. And in winter, north pole is tilted away from the sun, and south pole is tilted towards the sun. Okay, so leaning away, leaning towards. Because of that, this is what happens. Okay, so this is summer. The rays of light are coming in from right to left. So I'm drawn parallel lines to show the rays of light. And this is Earth with its axis tilted. So North Pole is leaning towards the direction of the sunlight. So it is exposed to the sunlight. So and then uh, one half of the Earth which is exposed to the light is daytime, and the other half is nighttime. Okay, so this red perpendicular lines here. So this the horizontal line is the plane of the ecliptic. It's parallel to the direction of the sunlight, and the perpendicular line is it's perpendicular to the ecliptic plane. Whereas this green line is the axis of rotation, and the other green line is the equator. Okay. So the green line makes 23 degrees with this red line. And the lines that I have shown here are the latitudes. So if I take this brown line at the top, So this latitude, all these points are within daylight. They're lit up. So as these points on this latitude go round and round the pole, they are always inside the daylight region. That means it is day always. Okay? And if I take a latitude which is slightly lower than that, okay, so that there I find that okay, so this yellow portion of the latitude is in sunlight and the black portion is in the night. So the major portion of the latitude is in the daylight. Okay, so that means where as these places as they go round and round, so they have a long daytime and a short night time. Okay, so as I come towards the equator, it's the same thing. Okay, so this for this other latitude, this daylight is longer than this. The daytime is longer than this nighttime, but the difference is less. Okay, not so much. And finally, when I come to the equator itself, okay, so here, if you see the day and night dividing line and the equator, they're crossing. So here, the day and night are same duration. Okay, so that's the one half of the green line is in night and the other half is in day, exposed to the sunlight. So at the equator, even in summer, day and night are same length. If you come to the southern hemisphere, so in summer, what happens is that the if I take this latitude, then the daylight portion is less than. Okay, so I take this entire latitude, this entire circle. So small portion of the circle is in the lighted region, daylight, and the larger portion of the circle is in the dark region. So night is longer. And if I come to the South Pole is totally in the night region, the dark region. So, and if I take this, this is the Antarctic Circle. So areas inside this, any latitude. So they're going round and round the axis, always rotating in the night region. So there is no light, there is no daytime. So when it is summer, the North Pole has continuous daylight throughout the day for a few months, and the South Pole has continuous night for a few months, right? So I can look at it like this. Okay? So I have this ball which on a knitting needle, that's the earth, and that's axis. So it's spinning in front of this light, which is the sun. Okay? So in summer, the axis is pointing towards the light. So you can see. So axis is okay. So this is in winter. Okay, so South Pole is pointing towards the sun, and the South Pole is lit up. Okay, so South Pole is lit up. Uh, and now I'm going to show you what happens between summer and winter. You have the equinox, the 2 days of the year which are equinoxes. So at that time, the axis is tilted in a it is tilted in a plane which is perpendicular to the direction of the sunlight. So this is what happens. Okay, so it's like this or like that. Okay, like that or like that. So when this is the case, when it is like that in you see when it rotates here, the day and night dividing that margin is passing through both the poles. Okay, so if I hold it correctly, it will go through both. So neither. Okay, so that means exactly one half uh, of every latitude is in daylight. So you have equal day and night when the axis is pointing in this plane, which is either when it is pointing this way or when it's pointing that way, but it's not leaning towards the sun or away from the sun. Okay? So the axis of rotation has not changed direction, but with relative to the sunlight, this is the situation because it has moved uh, to the different spot in the orbit. So this is what happens. So you have this is the equinoxes. Okay. So now we come back here. So this is the summer, and this is not just any day in summer. This is June 21st. 21st of June is when the Earth is at the extreme end in its orbit. So, okay, so you have in the northern hemisphere, you have long days, short nights, and the difference between day and night gradually decreases and at the equator, the difference is zero. Okay, and further down, when you go to the southern hemisphere, then the night is longer than the day. Okay, so 21st of June is called as the summer solstice. This is when it happens. It's a peak of summer in the northern hemisphere, and it is a peak of winter in the southern hemisphere. So in the northern hemisphere, you have the longest day of the year and shortest night, and in the southern hemisphere, it is the opposite. And so in winter, this is the situation. So if you compare these two diagrams, this axis is pointing in the same direction, axis of rotation, only the sunlight is coming in from different side. It's coming in from this side. Okay. So now the North Pole is pointing away, South Pole is pointing towards it. So in this Arctic region is totally in the night side, and the Antarctic region is totally in the light. So it has a continuous day. And this brown line, this divides the day and the night. And the other brown line, uh, this is the ecliptic. Okay? It lies in the ecliptic plane. So in December, we have this is what we have. So we have in the northern hemisphere, we have winter, and we have short nights. So 22nd of December is the winter solstice. So it's a peak of winter in the northern hemisphere. You have the longest day of the year in the northern hemisphere, and the opposite happens in the southern hemisphere. And on equinoxes, we have seen that the Earth's axis points neither towards the sunlight nor away from the sunlight. It is in a plane which is perpendicular. So you have exactly one half, the day and night are equal throughout, all over Earth, all over the Earth's surface. And so what are the dates of the equinoxes? Spring equinox happens on 21st March. So this is between so going from winter towards summer. Okay, so December, January, February, March. Okay, then June is summer solstice, and then July, August, September. September is the autumn equinox. And the sun shines directly overhead at noon on equator. Along the equator, every place along the equator has directly overhead sun at noon time. Okay. So what makes summers warm and winters cold? So now we have seen what explains the difference in the length of day and night from summer and winter. Okay, so but why do we have cold weather in winter and warm weather in summer? And why do the higher latitudes have very cold winters and and then they have mild summers? Whereas if you come close to the equator, then you have there's no difference in between summer and winter. So winter is not cold. So why is that? So to answer that, let's look at this. Okay, so I have a flashlight here, this blue, this is a flash bulb, and I'm pointing it on the surface of a table. So here I'm pointing it directly down, vertically down. So this is how the light spreads. So it's quite a compact spot of light. Whereas here I've tilted the flashlight and the light spreads over a large area. It's a very large spot. So the small spot of light is very intense and warm, whereas this large spot of light is very diffuse and cool. So the same thing happens when the sun's angle is sun goes high up and beats down on you vertically, then the energy that comes out of the sun is concentrated in a smaller area and it is warm. Okay? Whereas if it comes at a very slanting angle, the same energy gets distributed over a large area and it becomes very cool. So that's the reason when in early mornings and late evenings you have very slanting rays of sun and those are very cool, right? But when the sun goes up in the noon, then it beats down and it becomes very hot. So this is what happens. So uh, at what angle does the sunlight fall on various latitudes? So how does this angle of the sunlight falling on Earth, how does it change with the latitude? So what about the inclination of the sun at noon time? How high does it go in the at various latitudes? And can we observe the journey of the sun? So we want to know. We know that the sun rises at different locations, slightly different locations, and then it follows a different path in the sky each day. Okay? So we want to track this path of sun in the sky. Okay, so how do we track it? With reference to our immediate surroundings. So wherever you are, if you look around, you see a circle around yourself. Wherever you stand on Earth, you see this circular piece of land, and you have four directions there, okay, and the point which is directly above you. So, what on the globe? What are the four directions? If you take any spot on the globe, what are those four directions? So, the circle of the land that you observe at any location is called as the horizon. So, you can stand at any point on the globe, and you have this horizon which you can see. So this is how it is. So I have this spot on Earth, and I've drawn an arrow upward. So depending on your height, you can see at a different amount of different patch of land around you. So this arrow pointing up is directly overhead you. Okay, so what do I mean by directly overhead? It's vertical at that point. So if you extend the vertical back, it goes straight to the center of the sun, center of the earth. Okay, so the vertical which is above your head, it goes to the center of earth below your feet. Okay, and depending on your height, so if this is where you are, then your eye can see so far because the light travels in a straight line, so it can go so far until it meets the earth. So you can see a circle. So what is the horizon that we are talking about? You can also look at it like this. So if this yellow pin on this ball is you standing here, and you can see this brown line all around you, that is the horizon. And once you have a horizon, you want to fix the directions in your horizon. So which is your east and which is your west, north and south. So for any spot on the globe, no matter where you stand, so here I have marked the spot in the red, in red. So what are the directions of that at that point, that spot? So the directions, okay. So this any point, so this red dot is at the intersection of some longitude and some latitude. So all points on this longitude, which are so no matter where you are, there is one longitude going through that point. So all points on that longitude which are above, going towards the North Pole, those are north of that red spot. Okay, so all those points which are above it, so those are the north points to the north. That is the north direction. For the spot in red, those are the, that is the north direction, and this is the south direction. So with the longitude going towards the south pole is the south, and the latitude going towards the east, and latitude, that is the east, and this is the west. Okay. So no matter where you stand on earth, you have a horizon, you have four directions, and you have a point which is directly overhead. Now let's see how the angle of sun at noon varies between summer solstice and winter solstice at some latitude. Okay, so I'm considering this is okay. So this spot here is on latitude 50 degrees. That's a very high latitude in some very cold country. Okay, so okay, so this is some spot, some location which is at latitude 50 degrees. So why? So because it's latitude 50 degrees, so on this, on the globe we have this red line here is the north south is the axis of rotation, and the line perpendicular, the red line perpendicular is the equator. Okay, and this green line here is the plane of the ecliptic, that is the direction in which the sunlight is coming. Okay, and the line perpendicular to that, there's a line which is perpendicular to that. Okay. So now the 50 degrees is the angle between the, if I draw a radius through that point where you're standing, then that line makes 50 degrees with the equator. That is why it is called latitude 50 degrees. Okay. Now, the angle between this green line, which is the ecliptic plane, and the equator is 23 degrees because the axis is tilted at 23 degrees. Okay. So, okay. So, and so then this blue angle here is 27 degrees because both these angles add up to 50 degrees. So this is 27 degrees. Now here I have drawn this vertical line. So wherever you are standing, the point which is directly overhead overhead is the vertical. Okay? And if I extend it down back into the earth, it goes to the center of the earth, right? So that is the overhead point, and this is the direction of the sunlight. Okay, and these green lines are parallel to each other. So if this blue angle is 27 degrees, the other blue angle is also 27 degrees because they are the corresponding angles. Okay, there are parallel lines and a line which is intersecting. So from basic geometry, so we know that we can say that the sunlight makes angle of 27 degrees to the vertical. So that means sun is at an angle of 27 degrees to the vertical. So it is not directly overhead. It's not above your head, but it is making an angle of 27 degrees in summer. Okay. So now we can, no matter which latitude, if theta is the latitude, in summer, on summer solstice day, the angle, the sun makes an angle of the latitude in degrees minus 23. This is the angle which it makes. Now, if you look at this diagram, this green line here is 23 degrees to the equator. That means it is latitude 23 degrees. And If I extend it, that's also the direction of the sunlight. So the sunlight is coming directly overhead at this latitude 23 degrees on summer solstice day. So this latitude 23 degrees on the north of the equator is called as the Tropic of Cancer. So sun is directly overhead on June 21st on all points on Tropic of Cancer. Now this is the lower, this part of the diagram is for winter. So in winter, everything remains the same except that now the sunlight is coming from the left. Okay, and so again this red line is the axis, and the equator is also in red. Okay. So if I take the latitude 50 degrees, so this point, it is here. Okay, so it is here. This point is here, same place. In winter, it is here. And now, if I look at the angles, so this angle between this radius at that place and the equator is 50 degrees, and then this is the ecliptic, so that is 23. So now this blue angle is 23 plus 50 degrees. Okay, and that is the same as this blue angle here. So that means the sun is at an angle of 73 degrees to the vertical. That means it is very low. Okay, so it's not directly overhead at all. It is quite low in the horizon. It's making an angle of 73 degrees. Okay, so that is why in winter at this latitude, sun is very mild because it doesn't go up at all. It's a very low it's very low in the sky even at noon. Okay, so this is at noon. Okay, so okay, so and also we can, what else can we see here from the winter diagram? We can see that the sun is directly overhead at this latitude 23 degrees to the south of equator in the southern hemisphere. So this place is directly under the sun on 21st of June. So this latitude is called, if I draw this chord, then that all those places lie on the Tropic of Capricorn in the southern hemisphere. So it is directly, the sun is directly overhead at noon on all these places, okay, on this latitude. Okay, so now we're just going to make a model which shows the path of uh, the sun in the sky. Okay. So we will do that in the next video. For this video, we will stop here. So now that we have seen, we'll just look at this models in the next video. We'll stop here for this video.